Hi, in this video we're going to start looking at a very important topic of closures. So let's talk about closures and free variables, and let's think back to what we did in a few videos ago. We're looking at non-local variables. So just as a reminder, let's say we've got this outer function that creates a local variable x, currently set to Python. Then inside outer, we defined another function that referenced x. It didn't assign any value to x, it just referenced it. So Python saw that when inner was created at creation time, which happens when? It will happen when outer is called, right? When outer is created, it doesn't create inner, because remember, the contents of outer don't get executed until the function is called. Just the creation happens. So inner's creation doesn't happen until outer is called. When outer is called, it sees this x when it's creating inner. And so it says, okay, x will be non-local. Again, we've done all that before. So this x and this x are the same. We sometimes said very loosely that this x refers to this one. But it's not a direct reference, and this is going to become really important when we talk about closures. And I'll explain that more in a bit. So this x and this x are the same. Then, after we've defined inner, we call inner from inside outer. And so this x refers to the one in the outer scope, right? This non-local variable x is also called a free variable. That's the more technical term. When we talk about these kinds of non-local variables, we also refer to them as free variables. Now we can call outer. And what happens when we call outer? We get Python rocks, right? It actually looked up the value for x. Now, remember, when inner was created, when outer was called, right? First thing it did was create inner. It didn't look up the value for x until inner was called. So at that point, that's when x was evaluated. Python saw that its value was Python, and so it printed out Python rocks. So I'm keep stressing this creation time and run time because that's really important. So when we consider inner, we're really looking at two things, right? We're looking at the function inner, yeah, because we've got the inner function, but we also have this x, right? So the inner function has its local scope, but x is not in the local scope of inner, it's living somewhere else, right? It's this free variable that's living outside of inner. So when we consider inner, in here, we're really talking about two things, inner and the free variable x. There's two things along with it, right? Because x isn't inside inner. So we have to consider that these two things kind of live together. They have to be bound together. And that's called a closure, right? And that's because we say inner basically encloses its free variables. So it's a closure. So now let's do something a little different, right? Instead of calling inner from inside the outer function, we're just going to return it, right? You can return functions in Python. It's just going to be a higher order function. So let's go ahead and do that. So it's the same code. The only difference is that I'm removing the call to inner and I'm just returning inner. I'm not calling it, I'm just returning the function. So we still have a closure, right? When we call outer, we are still going to have a closure, inner plus its free variable, right? So we have those two things. Now this happens when outer runs. Then the closure is created. But inner is not called anymore inside outer. Instead it's returned. So we have this closure. What are we returning when we say return inner? We're returning the closure, not just the function bare of its free variables. It's the function plus its free variables. It's the function plus a little extra bit, right? So when we return inner, we're returning the closure. We have to consider that. Now we can assign that return value to a variable name, right? When we call outer, we get a function back. We get a closure back, but we get this function with its extra variables. So we can assign it a label, fn. So now fn is that closure. And if we call fn, since fn is really nothing more than inner with the free variables, it will print out Python rocks. Kind of makes sense. But does it really? Okay, so when we called fn, remember that Python doesn't evaluate x until it needs it, which means when we call inner, then it will go and look up the value for x. So it's going to look at the value for x. Where is it going to find x? X was a local variable in outer. When we called inner from inside the outer function, that kind of made sense that, yeah, Python sees this x, so it just looks, finds it in outer, and then it says, oh, it's equal to Python. But in this case, when we call fn, by that time, outer has finished running, right? It's finished running. Its scope is gone. How can fn now go ahead and see, oh, x equal to Python in the outer scope? The outer is gone. And yet, it still worked. It still retained its value, right? So that should be weird. That should sound odd. It's like, what's going on? How can it possibly retain that value of x, right? Even though the function that defined it, the scope where x was defined, went away. Well, that's because of that closure. That closure captured this variable x, right? And so it did something a little special to handle it, so that when outer finishes running, the closure still has whatever that variable was. So let's take a look at how that works. And we're going to take a look at Python cells and, in general, multi-scoped variables. What happens when you have a variable that is inside two scopes, as we have here with the closure, right? The variable inside the inner function and the variable in the enclosing function. Two different scopes, same variable. So it's shared between those two. So we say that that variable has multiple scopes. So just to keep it very, very simple, here we have outer, x equals Python. We have our inner function, which prints x. X is a reference to the outer's x. So therefore, inner and x is a closure, right? So the value of x is shared between two scopes, the outer function and the closure, the inner function. So this label x is in two different scopes, but it's really the same x, right? It has to be the same x. So that's kind of weird, right? It's this x label. We have to differentiate between the label and the value. So the label is in two different scopes, but the value that it's referencing is the same. How does Python do that? Well, Python does that by creating an intermediary object. And so here's how it does it. We're going to call this a cell. Python calls this a cell. It's an object that has a memory address, just like any object. But what it does, it basically contains a reference to another object. And that object is our string object that we set x to, right? And it has a memory address and a value of Python in this case. So what happens is that under normal circumstances, if we didn't have inner and print x here, right? If we just had def outer x equals Python return x, for example, then what would happen is that x would be a pointer directly to this object here in memory, the string object. However, here, because we have a closure, because we have a shared variable, right, between two different scopes, Python sees that and says, oh, okay, I need to do something special here. And it creates this cell. And now what happens is that the x in the outer scope, right? So I'm writing it as outer.x. Don't think of this as object notation. It's not. I'm just saying this is the x in the outer scope. Points to this cell. And the cell, in turn, points to the string Python. And the inner x, the x inside inner, does the same thing. It points to that cell. And that cell, in turn, points to Python. And this is what happens when you deal with non-local variables, right? This has nothing to do with just being a closure. It's just that you have a variable in two different scopes. So thinking back to when we discussed non-local variables, and remember we were thinking of chaining things, and I said, well, it's not really a chain. It's really pointing to the same object, but I didn't really explain how can it point to the same object. It points to the same object by using this intermediary, this cell. That cell is going to have the same memory address. In this case, I took an example, A500. So the real memory address of x is A500. The real memory address of x here is also A500. But when we refer to x, when we want to get the value for x, for example, then Python is going to use this indirect reference. It's going to essentially do a double hop, right? So the variable x in outer and inner point to the same cell, but Python knows that we're dealing with a cell, and so it will go and look at the indirect reference. So you can think of it that way. It's double hopping every time we retrieve the value. And then when we work with setting the value, it will be the same thing. We'll be changing what this cell points to, right? So if we had non-local x and x equals hello, then what would happen when we called the inner function that gets returned is that it would change what cell points to now point to hello, right? Because it's a shared variable. So the value changes, but Python is able to keep track of what's what by using this intermediate cell. So now you should understand why when that outer function finishes running and we call the returned value, it still knows what x is, because it still knows what cell is. Cell, right, didn't go away. Cell was the reference that outer x pointed to. When outer finished running, this goes away, but inner.x still points to the same cell. That object is still referenced. It's not garbage collected yet. All right? Okay. So now, sometimes you want to think of closures in more practical terms. You kind of need to remember that whole cell thing, that whole indirect, right, way of getting to the value, because it helps understand how variables are shared, what happens with shared scopes, right? It will help you kind of, keep that straight. But very often we just think of it, we say, hey, it's the same variable. However Python does it, yeah, it uses this intermediate cell, that's fine, right? But so you think of the closure as a function plus the free variables, that extended scope that contains the free variables. Now the free variables values is the object that the cell points to, right? So that could change over time, right? The cell address won't change, but what it points to can change. So every time the function in the closure is called, then, and the free variable is referenced, then Python looks up the cell object that the free variable points to and does the double hop, right? It basically does that double hop to see, okay, what's the actual value? But it doesn't do that until you call the function, right? When you create the function, it's just creating the pointer to cell. And then when you call the function, it does the double hop to look up the value. So in this case here, right, let's say we have this function outer, has a local variable a is 100, local variable x equals Python. Then we define a function inside. It also defines a equal 10, but you'll notice there's an assignment. I didn't say non-local, so a is a local variable to inner. It's not the same a as the one in outer. We've seen that before. And then we print something that references x. Well, this x wasn't assigned a value, so Python, when inner is created, says, aha, this is going to be a non-local variable. In other words, inner is a closure, and it's going to create that double hop. So a is going to be a direct pointer to the object 100, but x is going to be a pointer to a cell, and this x is going to point to the same cell as well, right? So this is our closure, and these two x's point to the cell, which indirectly references the string Python. You'll notice that a is not part of the closure, right? Because a is a local variable here and a is a local variable here. They're not the same a's. They're not part of the closure, therefore. Okay, so now we can call outer and assign that to fn. And outer is going to return what? It's going to return a function, right? So this function is going to be what? Well, it's going to be the inner function that gets returned. But remember, this is a closure, so it really also includes its captured variables, its extended scope. So it includes the free variable x, which again is what? The x, this free variable x in this closure is, remember, this cell over here. And Python will know to do the double hop when it needs to evaluate x when it does the print, then, right? So at this point, it hasn't evaluated x. Right now, it just said, okay, here's inner, and it has this variable x that points to this value here, right, to this cell. When we call fn, right, if we call fn, then it's going to execute inner, and then that will print out Python rocks, as we saw before. At that point, x will get evaluated via the double hop, and Python will come back, and so we'll print out Python rocks. Okay, let's look at introspection. So again, same example as before, right? So remember, again, we have these, this x is part of the closure, therefore it's pointing to a cell. and indirectly is referencing Python. So we run outer, we assign it to fn. And we can look at this property called dunderCode, and that dunderCode property itself has another property called free variables, co-free-vals. That will give you a tuple listing out all the free variable labels that are in use. In this case, it tells us x is a free variable, and that's the only one, because a, you'll notice, is not a free variable. Now we can also call fn _dunder closure. That's kind of an interesting one. That's going to give us the following back. It's going to give us that this is an object. So again, it's going to be a tuple because there could be more than one free variable in the closure. But it's going to contain in the tuple this cell object, the same cell object we talked about. And it's going to tell us the cell object is at this memory address. And you'll notice that's the same memory address as this one here in the diagram. And it contains a string object. It's pointing to a string object at some other memory address. Yeah, this one over here, right? So when you do dunder closure, it actually tells you exactly what's going on with your free variable. And if you got more than one, you'll get, multiple entries in the tuple. Now, the one thing I was telling you about this double hop is that, one of the reasons why you don't really have to think about that double hop all the time is because Python takes care of that for you, right? So when we're in here, when we print x, Python knows that, yeah, x is in this cell at A500, but I need to go and look up the value at FF100. And so it does that automatically. We don't have to think about it, and so we get Python rocks, right? But now what's interesting is, what about the memory address of x in the outer function and the memory address of x in the inner function? What are we going to get back? Are we going to get back the cell? That's technically what x is pointing to. Well, again, Python does kind of some heavy lifting for us. Not that we really need to work with the memory addresses, but still it's useful for debugging purposes to know, well, what object is x pointing to in the double hop? So that's what Python gives us back. It gives us the indirect reference back. So if we print hex of ID of x here, we'll get FF100, which is the object that contains the string Python, right? This one over here. And the same thing inside the inner function, it will give us the indirect reference, right, to the Python object. So it's kind of hidden from us, right? It's very opaque that Python is using this intermediary cell. But it is doing that. You should think of it that way, and that will help sometimes figure out what's happening with scopes. Okay, how about modifying the free variables? Well, remember when we did non-local in one of the past videos, right? We were able to basically change the value of the non-local variable count, right, in this case. So here's a very simple closure, but pretty prototypical of what you might do for closures. So here's this counter function. It creates a local variable called count. Then it creates a function inc, right, or defines a function inc. And the function inc says, I'm going to use this variable count, and it's going to be non-local. When counter is called, right, when it's called, at that time, inc will be created, and count will be a non-local variable, which means that Python is going to create a cell, and count in counter and count in inc are going to reference that cell, right? Just as we saw before. So the closure, the free variable is count, so the closure is inc and count, right? Count's the free variable, it's bound to the cell count. To the cell, right? Not to the variable count, not to the object that count was pointing to that cell, because it's a free variable in a closure. So when we call counter, we get the closure back, right? We get inc and count. So fn is the closure, inc and count, which is currently 0. So when we call fn, what do we get back? Well, initially count is 0, right? So when we call inc, what happens? It says count is equal to count plus 1. So count is equal to 1, right? Sets it to 1, returns count, and we get 1 back. Makes sense, right? Count's indirect reference changed from the object 0 to the object 1. If we call fn again, we get 2. Well, yeah, count was 1. We add 1 to it, that's 2, and then we return that, so we get 2 back, right? Okay, what about multiple instances of closures? And that's really, again, important to understand, but if you understand when that cell is created and how it's created, then this is very easy. So every time we run a function, a new scope is created. So if that function generates a closure, well, a new closure is created every time as well. Let's look at an example of what that really means. So just going to use the same example as before, right? This is our closure. And now we're going to call counter and assign it to F1. We're going to call counter and assign it to F2. Okay, what happens when we call counter? Well, when we call counter, it creates at that point the closure, right? Because we've called counter. So it creates inc and the closure. But now, because count is a free variable, count is going to point to some cell, some memory address somewhere, okay? And then we return the closure and assign it to F1. Now we call counter again. Well, this is now a different call to counter. It has its own local scope and it creates its own closure. So guess what? The cell that gets created with the free variable count in the second time around, well, that cell doesn't have the same memory address as the first time it was created, right? There's no reason why it should have. So we have two different closures that don't have a shared scope, right? That cell that's being used for count has a different memory address with F1 and F2. And in fact, if you do F1 dunder closure for F1 and F2, you'll see that the cell doesn't live at the same memory address. Even though you might notice the value that both cells point to is the same, right? Because remember that 0 is just going to be a singleton object. If you don't remember that, go back to some of the earlier videos that we had on integers and how some of them are stored and pre-built into memory as singleton objects. Okay, so when we call F1, what happens? Well, we get 1, right? Same thing as before. If we call F1 again, we get 2, and then again we get 3, and so on. What happens when we call F2? It's its own closure. At this point we call F2, what's the value for count? It's 0, right? We call F2, count is currently 0, right? It's a different scope, and then it adds 1 to it, so it's going to return 1, all right? So F1 and F2 do not have the same extended scope. They're different instances of the closure because they were created inside different scopes, right? Every time we call a function, a new scope is created. And if the closure is created in that new scope, well, obviously the closures can't have the same scope. And that's because the cells are different, are created differently from one call to the next. So can we share extended scopes? And the answer to that is yes. Let's see how we might do something like that. So let's say we've got this outer function and we have a local variable count. And then we create this function here called inc1, which references count as non-local. So that's a closure, right? So right away we know inc1 is a closure. Count here and count there have the same cell reference, right? They reference the same cell. So count's the free variable and it's bound to count in the extended scope. But inc2 does the same thing, so it also is a closure and its count is the same as the count that's out here. In other words, what's happening is that this count is pointing to the same cell as this count, and this count points to the same cell. So all three counts are pointing to the same cell. So you can see that count inside this first closure and count inside that second closure are the same, right? It's the same count. So we have a shared scope right there, right? Or a count is shared between multiple scopes, not just outer, it's shared between these two closures as well. And now we can return the two closures in a tuple. So if we do that, then we can call outer and unpack the tuple into the labels F1 and F2. F1 is going to be the closure inc1 and count, and F2 is going to be the closure inc2 and count, but the count is going to be the same between the two. So now if we call F1, we get 1. If we call F2, what do we get? Well, it's the same count, right? So when F1 is finished running, what's count equal to? 1. When we call F2, at that point, when we call F2, we're calling inc2. At that point, when we say count equals count plus 1, Python goes and says, oh, I need to look up the value for count. So remember, I was harping upon that right in the beginning. You've got to understand when is the closure created versus when are the free variables evaluated, right? The closure is created when the function is created. That's when Python decides it's a closure, it's going to use that cell, and it's going to do the double hop eventually. But it doesn't actually evaluate the value of the free variable until you call the function in that closure. At that point, it runs the function and then it needs to evaluate count in this case. So when F2 is called, then it needs to go evaluate count. But count's already 1. So it's going to add 1 to 1, that's going to be 2. It's going to assign it to count and then return count, which is 2. So when we call F2, we actually get 2 back. So that's an example of how you can share the extended scope between two different closures. Those are two different closures, but they have a shared free variable. So you might think that, well, this is kind of highly unusual, right? I mean, how often are you going to do something like that? Probably not that often. Well, it actually happens a lot more than you might think, and it happens by mistake. I think that's the main thing. That's why I want to point it out, because it's very easy to fall into a trap here. And let me show you what I mean. Let's say we want to create this function adder. So adder is going to take a parameter n, and it's going to define inside another function inner that itself takes another parameter x, and it's going to return x plus n. So essentially I'm adding two values together, but I'm using a closure to do that. Okay? So what's the closure? Well, in this case the closure is inner and n, right? Because n is being referenced, but it's the one that's in adder. So the closure is inner and n. This n and this n point to the same cell. Okay? So now I can call adder with a value of 1. So this is going to give me a closure, which is going to be this inner function, with n pointing to some cell that currently points to the value 1. I can call adder again. It's going to return another function, inner, right? But this time it's going to point to another cell that is itself going to point to some object that contains the integer 2. And then the same thing with 3. So in fact, when we call add1, it's going to add 1 to whatever we pass in as the parameter for add1. Because remember, add1 is just inner. So it expects one parameter as well, right? The point though is that those are three different closures, no shared scopes. They were created from different calls to the function. Different scopes, therefore different closures. So if we call add1 on 10, right? X is now 10, and it's going to say, okay, well, add1 x closure, the value for n, what is it? Oh, it's 1. Okay, add 1 to it and return it. We get 11. When we call add2 on 10, Python says, okay, what's add2? Well, it's the closure add, right, inner, with n equal to 2, different cell, and its reference is 2. So, okay, I got to add 2 to x, and returns therefore 12. And the same thing with add3. It returns 13. So far, no shared scopes, right? Good. The only thing is though, as soon as you start writing code like this, add1, add2, add3, you notice it's so repetitive. Immediately we think of loops, right? We think, well, I don't want to write the same thing more than once, so I'm going to write a loop. Now in this case, I probably wouldn't for three times the same thing, and it's such easy code. But you may have more than that, or you may have something more complicated, and it's like, I'm going to write it in a loop. Okay, fair enough. So we can do that. But there's a caveat. Let's say we tried it this way. So I'm going to create this empty list adders, and essentially adders is going to contain my closures, and I'm going to build those closures inside a loop. I'm going to create a loop for n in range 1 through 4. So it's going to go 1, 2, and 3, right? n is going to start at 1, and then the next iteration, n will become 2, and then n will become 3. You'll notice I'm saying n will become. It's not creating a new n every time this iteration runs, right? Every iteration, it's still the same variable n, it's the same label n, it's just that it's going to point to different values, 1, 2, and 3, right? But it's still the same label n. Okay, so now we still need to create the adder function. So we're going to use a lambda expression, and what does the lambda do? Well, it's going to take in a single parameter x, just like that add, that increment function did, and we're going to return x plus n. Now n is not defined as a parameter for lambda, so n is a free variable. We've just created a closure. And what do? We then append it to the adders array, to the adders list. Now, a side note. There's a misconception that lambda expressions are the same thing as closures. They're not. Lambda expressions just create functions. A function is a function. A function only becomes a closure if it has a free variable. Lambda expressions are functions. They don't have to have a free variable. If they don't have a free variable, they're not a closure, right? So the thing is that we often create closures using lambdas, like in this example here. And so very often, lambdas and closures are introduced at the same time, but they have nothing to do, right? A lambda is not necessarily a closure, and a closure is not necessarily a lambda. Closure just means this extended scope, right? That concept we talked about. Okay, so what's happening here? Well, the free variable is n. What n is this? Well, it's obviously not the n inside the scope of that lambda function, because it wasn't defined in there, right? So it has to be from the outer scope. Which outer scope is that? Well, this one out here. So it's this label n. So this n and this n mean the same thing. So what happens? A cell now is created, and this n points to that cell, and that n points to the same cell. And that cell currently points to the value n equals 1 when we have our first iteration. So when n equals 1, the free variable in the lambda is n, and it's bound to the n that we created in the loop, essentially, right? Now when we run n equals 2, what happens? Well, again, we create another closure, right? X plus n equals 2 now, but what does that mean? It means that, remember, n is going to point to the same cell as the n in the loop, right? And then it's going to set that n equal to 2, right? Because n equals 2. So what's happening is that it's bound to the same n we created in the loop, but n equals 2 now, right? We set n equal to 2 in the outside scope. But all it does, remember, is that it changes the indirect value. The direct value, the direct pointer of this n and this n that was created in these two different loops is all pointing to the same cell. And if you do that again a third time, same thing happens. It's bound to the same n, which means it's bound to the same cell, but now the cell is pointing to a new value, n equals 3, because we changed the value of n in the outside, right, in the external scope, in the enclosing scope, to 3. So now we have three closures that each have this free variable n that are all pointing to the same cell, and the n in the for loop is also pointing to the same cell. So now you can hopefully see the problem, right? I can call the closures this way, right? Because I've got my 3 closures in the adders. When we call the last one, we get 13 back, 10 plus 3, that's what we expected. But if we call the first one back, we also get 13. Why? Well, n was changed to 3 in the very last iteration. So now all the n's are pointing to one cell that points to 3 now, because we changed it to 3 when the last iteration ran. And remember, when does n get evaluated? And I keep going back to that because that's important. That n gets evaluated when the closure is called. So when we call adders 0 on 10, at that point, Python says, okay, what's n? I need to know what n is. Oh, n is an indirect thing. Go to the cell points to 3. Okay, it's 3. So return 10 plus 3, it returns 13. And you get the same thing if you add 1, right? So I've seen this problem come up again and again in various discussions online. And this is why. It's because of that cell that gets used when you have a closure, right? And in this case, we're sharing it with this n out here, which is the same n. So it's a shared, these free variables are sharing, right, the same cell. So not uncommon to get into situations like that. All right. The last thing I want to talk about are nested closures. We can nest closures. We can nest functions, right? We saw that. We had one level of nesting, outer and inner, but you can nest multiple levels. So let's see what I mean by that. Let's say we have this incrementer function. And basically, I want to kind of expand on the increment closure that we had, where, remember, the count was just set to 0 inside the counter, the outer function, right? And then the increment function just added 1 to it. So what I want to do is I want to be able to set the start value and the step value for something like this. So a very simple way of doing it might be this. And here we're going to define this incrementer, and the incrementer is going to take in the step value. So n is going to be the step. And what does incrementer do? it defines inner that itself takes in a parameter start. Okay, so n is local to incrementer, start is local to inner. And here I set current equal to start. That's just because I want to rename that label. So just to keep it more consistent, or at least for it to make more sense inside the now nested function below. And the next thing that I do inside inner is I create another function, right? So you see now we're 2 levels deep. And I say non-local current. Well, which current is that? Well, it's this one over here, right? So inc has a free variable current. Then I say current equals current plus n. I haven't assigned n, so Python looks at that and says, well, that's non-local, and therefore this is a free variable as well. So if you look at inc, right, the closure is inc with current and n. That's the closure. Current lives here, and where does n live? N doesn't live in inner. N is actually lives in incrementer. That's where it was defined. It was the parameter to incrementer. So this n and this n share the same cell, and this current share the same cell, right? Should be pretty straightforward to understand what's going on. So now let's look at what happens when we call incrementer and we give it a value of 2. Well, we've just called incrementer. What is it going to return? It's going to return that inner closure, right? That inner function with the closure. But what's the closure of inner? Well, it's inner in n, right? So if you look at the free variables, the free vars in Python, it will give you a tuple with a single element, n. And the current value of n is 2. So now fn is itself a function that we can call. It's this inner function. So we can call it with a start value, let's say 100, right? So what happens here? Well, it's going to return inc, right? So it's going to return another function, another closure. What is the closure? Well, the closure is current and n, right? Because we're referencing current and n. So the free vars will tell you it's current and n. Now, you'll notice that inner, right, well, the inner closure included n. Even though we didn't reference n directly inside inner, we still referenced it within inner, but inside another function. That's still inside the inner function. So n is still, a free variable in inner. Even though it's not used directly in the body of inner, it's used indirectly inside this nested closure. But it's still there, right? So currently current is 100 and n is equal to 2. So now if you call inc2, what happens? Well, current is 100, n equals 2. What is it going to do? It's going to add 2 to it and return it. So it's going to return, it's going to call inc, and it's going to return 102, and then current will now be 102, and n stays at 2. And if you call it again, you'll get 104, current will be 104, n will be equal to 2. So nested closures is actually pretty common. It's something that we'll see when we get to decorators later on in this section. We'll start with simpler decorators that don't require nested functions. They do require closures, but we'll see where we might start requiring nested closures in order to do certain types of decorators. All right, so thanks for watching. It's an important topic. It's been long. Take a break and then come back and we'll dive into the code. So thanks for watching, and I'll see you in a bit.